So it's my pleasure to introduce Stephanie today. Stephanie, I guess I had the pleasure of having her as my first student. I don't know if she could say the same about, if she could say being my first student was a pleasure. But yeah, so I don't know if many of you guys know this, but when Stephanie started college, she started in art, and she loved being outdoors, and she decided to major in wildlife biology, which is lucky for us. She got her BS in wildlife biology at Humboldt, and while she was there, she started to work on a project monitoring seabirds at Castle Rock. So she started working on that project in 2009. And I'm not going to say much about it today because that's what she is presenting. She continued to work on that project for years, a couple of years, before she decided that she wanted to go back to grad school, learn a little bit more on how to develop projects and analyze her data. So she was looking into graduate programs, because she told me this the other week on our walk. She wanted to work with someone well-established and experienced and knew what they were doing. So she contacted Jim. And she came and she met with Jim, and then Jim let her know that they had hired me. We had a Skype interview, and one of the things she probably doesn't know is that I was probably more nervous on that Skype interview than she was, because I'm like, how in the hell am I supposed to know if this is going to be a good student or not? Like, her application looks great, but what questions do I ask? But after that interview, I had no doubt. Her letters of recommendation were awesome. Her application was a solid package. She came with a really amazing data set. So I decided to take a chance, and I do not regret it. I could not have asked for a better first student, and that's saying a lot because all of my students are pretty awesome. So she came to Moss Landing. She actually got here before me, so she's been here longer than I have. So when I showed up, she helped me figure out what I was supposed to do. And she really worked with me and was patient with me as I kind of figured out how to do things. So a lot of times you'd be like, I don't know, who has to be on your committee? Let's read the manual together. So for those of you that came after her, if it was at all smooth, you can thank Stephanie a little bit for that. She also was she TA'd for me on 3 different courses. So for those of you that took the stats class when it switched to R, you can actually thank her for that, because I don't know if I would have had the confidence to make that switch without her willingness to kind of step up and help the students when I was making that transition to R. So basically, I know there's a tradition of roasting people, but apparently Stephanie doesn't do embarrassing things. We couldn't find any pictures. The only pictures we could find was her working. So we had to kind of make up her own. In the lab, her nickname is the snow leopard, very elusive, and so this ended up being very appropriate when I was trying to track down pictures. But with that, I just want to introduce Stephanie and say I'm excited for you guys to hear what she's been working on for the past few years, and yeah, so that's it.
Thank you very much. I don't think I could ask for a better intro. And thank everyone for coming to see this. As Gita said, it's been years in the making. So just to start, I'll read the title. Today I'm going to be talking about the reproductive performance, foraging effort, and diet of an apex predator, the common murre, at one of the largest nesting colonies in the California current system. So to begin, I want to talk a little bit about apex predators. These are organisms that forage at the top of the food chain, and they play a crucial role in maintaining the balance of food webs by exerting top-down pressure on their prey. These predators also require an abundance of energy to survive and reproduce, and are therefore reliant on productive ecosystems. So, at the base of the food web, on land and in the sea, is the sun, and it's often represented with a pyramid, which I'll get to in a second. For marine predators, the base of the food web is phytoplankton, which a lot of us are familiar with. And basically, the amount of energy that transfers to the next trophic level on average is about 10%. So about 10% of the energy at the base of the food web will move up into the next level, which would be zooplankton and other invertebrates. And then another 10% will go into the ichthoplankton and fish fauna, and then only the remaining 10% will be available for apex predators. So what's available at the base of the food web is going to dictate how much energy is available ultimately to the things at the top of the food web. So these predators are basically reliant on productive ecosystems. And the ocean kind of all looks the same, but a lot of us know that there's areas of the ocean that are more productive than others. And some of the most productive areas of the ocean are in eastern boundary current systems. And what happens in these areas is a seasonal shift in winds such that it causes nutrient-rich water to upwell from the deep. And one of these eastern boundary currents is right off our coastline, the California current. So to kind of illustrate how this upwelling works briefly, this is just a stretch of the California coastline. And in late winter and early spring, winds going from north to south kick in. And what happens due to Ekman transport and the Coriolis force is water at the surface gets pushed offshore, and this more nutrient-rich deep water can upwell. And it's not immediate, but what happens is these nutrients become available for phytoplankton blooms, and it takes about 4 to 7 days on average for phytoplankton. And then some more time passes, and that becomes available for zooplankton to take advantage of. And eventually, there are enough zooplankton to support fish populations. And then there's enough food for these larger organisms that require an abundance of prey. So productivity varies across the marine system, and this is in space as well as time. This is just a seasonal progression of upwelling along the coastline, with red being warmer and green being cooler waters. So you can see how variable it is, even in a small California-specific region along the California current system, this cold, nutrient-rich water. So this variability in upwelling can have orders of magnitude differences on primary productivity, and this variability will permeate through the food web, which results in dramatic fluctuations of the abundance and composition of prey. And marine predators must be able to cope with this variability in their preyscape, and understanding the mechanisms by which they do so and the limits to their ability to compensate provides insights into their ability to withstand changing marine systems. So different apex predators have different ways of dealing with this variability. So for example, sharks and other exothermic organisms don't have a very high metabolism, and they can eat a meal in a productive area and then go for a long period of time without feeding. Other apex predators, such as marine mammals, can store huge reserves of fat that travels around with them, so when they can't find food, they can tap into these fat reserves. And many marine mammals actually have life cycles that incorporate fasting just to deal with the lack of food at certain times. Seabirds are kind of unique. They have to be able to travel. Well, they have high metabolism because they're small and they maintain their body temperature, but they also have to be able to fly, so they can't get very fat. So seabirds need to be eating every day pretty much, or else they're going to starve. Some seabirds can travel far to productive areas, but others aren't really good at flying, so they have to kind of constantly exist in this productive region. And because of this, their reproduction, foraging effort, and diet depends on and rapidly reflects the abundance and composition of prey in the marine environment. So for seabirds, the breeding season is the most energetically demanding part of their life cycle, and having sufficient prey during this time is critical to a successful outcome. So when seabirds aren't nesting, they could be anywhere in the marine environment. So for the majority of the year, they can feed and exist where prey are most optimal. But nesting requires that they congregate on a few limited number of offshore islands along the coastline. So right away where they can eat is restricted. So in the California current system, currently there are 2 islands that support more than 100,000 breeding seabirds. This is the Farallon Islands to the south and Castle Rock National Wildlife Refuge to the north. And one mechanism by which birds nesting in the California current system, like I hinted at earlier, is to ensure that they nest at a time when peak energy will be available for when they're raising chicks. So for the California current, that's when the upwelling, when the seasonal winds that drive upwelling begin. So once nesting initiates, seabirds become central place foragers. And what that means is they can only go so far from the island before they have to return to incubate their egg and feed chicks. And because of this, foraging areas accessible to seabirds are drastically reduced relative to non-breeding periods. And basically, they are, for the duration of nesting, seabirds are completely reliant on the water that's within flight distance of their breeding colony to meet the needs of themselves and their young. So, yeah, basically, the prey community within flight distance of the breeding colony will determine when seabirds should initiate nesting, if they can meet the energetic needs of their young, how hard they must work to do so, and what prey types they can find. So this is the common murre. It's a piscivorous pursuit diver, which basically means it goes underwater and grabs fish. And this is the most abundant breeding seabird in the California current system. Like other seabirds, their reproduction, diet, and foraging effort are going to be reflective of variability in the local prey community at various time scales from days to weeks and even across years. And understanding these metrics allow us to identify mechanisms underlying changes in their abundance, gain insight into their population health, and facilitate a baseline development of what is normal in a given region. So this idea of what's normal is good to understand so that in the future you can say things have changed or they've stayed the same. So one really cool thing about common murre is they are easily observed at the colony, and they're active during the day and they nest above ground. And these little gray spots are actually hundreds of thousands of common murre. So if you could be there, it would look like just a big pile of murres. And the cool thing too is they actually bring whole prey to the colony. So you can, in theory, if you can see well enough, you can see what they're feeding their chicks right at the colony. So all these characteristics make murre an ideal candidate to learn about their reproduction, foraging effort, and diet all in the same colony-based setting. One thing I want to kind of talk about, this is a relationship between foraging effort and time allocation. So for murres, you know, if you're a bird, you're going to go out in the ocean and try to find prey for your chick. And if there's a lot of prey, it's going to be relatively easy to feed chicks. And then if there's not a lot of prey, you're going to have to work harder, and it's going to become more difficult to feed chicks. So there's a relationship with that and how it looks like at the colony. So at the colony, when prey are abundant, for murres, adults can spend up to 50% of their day, 40 to 50% of their day with their chick. And then as prey become more scarce, they'll reduce the amount of time they spend together, leaving one parent with a chick. And in times of extreme prey scarcity, they'll actually leave their chick alone. But bad things can happen when you do that, so they have a strong motivation to not have that happen. And these conditions are kind of rare. Most colonies see about 10% or more of the time murres spending together with their chick. So, as a brief background of colony-based studies of seabirds in the California current system, despite its importance to murres and other seabirds that nest here, Castle Rock National Wildlife Refuge has received little attention beyond aerial censuses, which basically you count the number of nesting adults. The Farallon Islands, on the other hand, has had the longest, most comprehensive colony-based study of seabirds in the California current system, with continuous observation since 1971. So, for a long time, the Farallones is about 400 kilometers to the south of Castle Rock, and for a long time, it just had been assumed that what was seen there could be generalized to a broader area, which includes Castle Rock, due to certain oceanographic similarities, but as studies go on and we get more higher resolution in our look at the ocean, there's more evidence that this area of the California current system is not as homogeneous as we once thought. So this begs the question, what about seabirds of Castle Rock? And are these assumptions of similarity applicable? Castle Rock is a huge breeding colony, and if it's distinct, differences between these two colonies could contribute to population level dynamics of murres across the California current system and determine the resiliency of the whole population to withstand environmental change. So the objective of my study was to establish a baseline understanding of common murre nesting at Castle Rock. This is an 11-year time series, and it was so long because the goal was to capture a representative variability in prey conditions. And specifically, we were interested in looking at the timing of nesting, the success of nests, how hard individuals are working to find food, and what they're eating. So a couple predictions that I had in terms of nest initiation, I predicted it'd be associated with upwelling. I predicted that nesting would be relatively successful, and the reason for this is because murres only lay one egg, and for seabirds that do that, once they lay an egg, they've kind of committed to making that happen. So they can't just have 4 eggs next year and 4 chicks next year if this year goes bad. So they have 1 chick, and they do their best to make sure it fledges. So at most colonies, murres have 70% or higher nesting success on average. And then prediction number 3 would be that there's a suite of metrics that reflect foraging effort, and so years that require more effort are indicated by pairs spending minimal time together, which is called co-attendance. Chick rearing murres potentially leaving their chicks alone so that they can maximize time looking for prey. Spending longer times per trip at sea to find food. Having trips be less successful, so coming back without a fish. And having an overall lower feeding rate for your chick. And then finally, a final prediction was that diet at Castle Rock may be distinct from other areas of the California current, but going into it, we didn't really know what we would find. So my role, Gita said, I've been working on this project since 2008. I started as a technician. And then also all the technical stuff that nobody really wants to talk about. And I've been overseeing the data collection since 2009. And basically, I've trained everyone that's worked on the project. A lot of VertLab people have worked on it with me. But in terms of nesting, in terms of most of the surveys, I had a hand in all of them and actually identified all the fish, which was kind of fun. So, study area. Let's revisit the slide that highlights the 2 major colonies in the California current system. So Castle Rock is the northerly one. And this island supports all 11 seabirds that nest in this area of the California current system. The focus of my thesis is common murre. So to make observations at Castle Rock, this is what it looks like from shore. And it's a bit too far. You can't see through spotting scopes enough detail to make any real conclusions about anything. And the ocean's pretty rough, so boat-based surveys aren't really an option either. The people before me were creative, and they installed a camera system on this precipice on the island. It basically has 2 daylight cameras and is solar powered. And the cameras I can control from this laptop, and they can rotate, zoom, basically do whatever you want them to do. This is a huge effort. Even we have to transfer batteries onto the island from boat. So we've had to come up with creative ways to actually pull this off. And like I said, it's really technical. So this is a diagram of the whole system. And I'm not really going to get into it other than, like, there's a lot of pieces that can break in any given year, and they do. So it's lucky that we've gotten as much data as we have. So this was an 11-year study, 2007 to 2017, and during that time, I determined that the nest initiation date for 821 nests, accurate to plus or minus 3 days. For a larger subset of nests, I figured out the reproductive success for 856 of them. To determine foraging effort, we followed 159 chick rearing pairs, and then 5,162 prey were identified. I put this in here because I felt like I'm supposed to say something about my statistical analyses in general. I'm welcome you guys to ask me any questions you want about statistics. When I'm comparing between years, I use ANOVAs unless it wasn't normal or had widely unequal variances, then I use bootstrapping. And then for nest success, I used a generalized linear model. And then for prey composition, I used basically a non-metric multidimensional scale. So, to the fun stuff. So, the nest surveys, this is what it looks like when we're looking at the island. And basically each bird within a certain area of the camera, so about 100 birds a year, we give a unique number to. And we can figure out how well. We look at them from before they lay an egg every other day till after their chick leaves. And we can note if an egg's there, a chick's there, and when the chick leaves, so we know exactly what happens to these nests. So for the timing of nesting, what we found is that it varies across years, so years on the x-axis, and then the date of nest initiations on the y-axis. And you can see it can vary by 25 days from the earliest year to the latest year. So to get at the question of what's driving this variability, which I've been hinting at, one way in which the timing of upwelling is measured is by basically for each year summarizing the upwelling index from the start of the year, January 1st, to the end, December 31st, and then on that summation, finding the minima of the curve. So if I break this into years, this is all the years of the study. Basically, for each year where it hits that minima early in late winter, early spring, is the date of spring transition. So this is only at the 42 degrees latitude where Castle Rock is. So I use these dates, which is on the x-axis, and then on the y-axis is the date of the first nest. And you can see that there is some relationship. It's about 35% of the variation in nest initiations described by this variation in spring transition date. I actually had a different method of determining spring transition as well, because what I just showed you really represents a physical spring transition, and I wanted to try to get at the biologically relevant transition to upwelling. So here I'm going to go back. But in this example, you can transition to upwelling when there's still this huge amount of downwelling pervading. So in 2010, it's well below 0, which is signifying downwelling. So what I did is basically I just use the 15-day running mean of the upwelling index. And so if it's above 0, it's upwelling. If it's below, it's downwelling. And I just smoothed this out just for you guys to visually make this easy to see. But I noted the date of spring transition as the time at which this upwelling index crossed 0. So the point at which upwelling became positive and remained positive for the seabird breeding season. And when you relate that to the date of first nest, it explains about 60% of the variation in the date of first nesting. So basically, that matches what I would have predicted, that nesting, to some degree, whether you calculate spring transition one way or another, nesting is happening in relationship to this transition to a more productive regime. And partly that's because females require a certain amount of energy to make an egg. So they can't make an egg if there's not enough energy. So getting into reproductive success, what we found at Castle Rock is, this is just the number of eggs laid over the number of chicks that left, so overall nesting success. And you can see it's generally above 50%. 2016 and 17, there was two not good years. And if you break it into the egg component and chick component, so hatching success is the ability of the egg to survive. It kind of reflects what you saw with overall nest success. And then if you look at fledging success, so once it hatches, what's the chance that it'll survive? Fledging success is a lot higher and it's pretty stable. So for these 2 years, it's low, and then for the remainder, if you exclude those 2 years, the average fledging success is 89%. So I'd say at Castle Rock, fledging success is pretty good, and I'm going to focus on fledging success from here on out because foraging effort to feed chicks and diet for chicks is related to the chick period. So in general at Castle Rock, we produce a lot of these fuzzy little chicks, and for purposes of, like, I know it's a lot of years, so I'm going to color code them. 2012, we didn't get data because the cameras failed early in the season, so we just had the initiation of nests. These are all relatively good years in terms of fledging success, highlighted in green. A moderate year, 2007, highlighted in yellow. And then the two not so good years highlighted in red, 2016 and 2017. So now to get at time allocation surveys. This is what the video actually looks like. So we point the camera at a group of Murres during a day, and we watch all the birds that we know about on the screen. So there is a bird arriving with a fish, and we would note the time, and we would know exactly what happens with that fish if the mates trade places and when the other mate leaves. So we can tell exactly how long they're at the colony and what's going on with those fish. Oh, and you can see that bird just stole the fish. That's not supposed to happen. So to go through the suite of metrics that indicate foraging effort, there's basically co-attendance, which is the time that chick rearing pairs spend together on the island. And you can see in the good years, co-attendance tends to be higher, around 5 to 6%. There are some good years where co-attendance is actually a bit lower and more similar to bad years. And then in the years where fledging success was low, co-attendance was also minimal, indicating that they're foraging pretty hard. 2017 is missing because actually all the chicks died in the first week, so I couldn't actually do a time budget survey, and I can tell you from what I saw, they were starving. So I assume they'd be foraging really hard in 2017 if the chicks had lived. But basically, even in the best years, this is very limited for Murre, so this is all below 10%. So if we look at the time that chicks are left alone, in all the years where fledging success was relatively high, chicks are not frequently left alone. 2011, they weren't left alone at all, but in all years they can be left alone in all years. And this is very rare. Chicks are not typically noted to be left alone. In 2007, you can see about 25% of the day chicks were left alone. And then 2016, the reason why this value is so low, you'd expect it to be higher because 2016 they had a really hard year producing chicks. And the reason why I think that is because we only got one survey in before all the chicks died, and when they're young, they don't need to eat as much. So if we could have done this later surveys, I assume MERS would have been working a lot harder to feed chicks at that point. So either way, just leaving chicks alone at all is rare, and leaving them alone for 25% of the day is not a common situation based on other studies. So the time spent searching for prey is the time per trip, and this is in minutes. So in most of the good years, they spend about 2 hours per foraging trip. These are still good years, but they were spending a little bit more time at sea in 2008 and 2015. And then in 2007 and 2016, they're spending a lot longer at sea. So this is 3 times longer in search of food in years with poor reproduction. And then in terms of their success of foraging trips, so then, when they go to sea, do they come back with a fish? In most years, they do. So that's all 80% and above. In 2016, not only did they have longer trips, as I just showed you in the last slide, they were also less successful. So they were going out looking for a long time and then still not coming back with food. And how that translates into chick feeding rates, so as you'd expect in the worst years, the feeding rates were lowest. In a good year, you also see the highest feeding rate, and then there's kind of all this variability in between. But basically, chicks are fed less in years with poor reproduction, and this coincides with years where they're also foraging harder. And the bottom line is food is essential, so this is the number of prey fed to chicks on the x-axis, and if the chick perished or survived. And you can see chicks that fail tend to get fed less than chicks that survive. And in fact, based on a logistic regression, with this data, if 75% of the chicks are to survive, they need to have at least 1.8 prey per day. So MERS have to be able to find food every single day for the whole chick rearing period, or else failure can result. So this comes to the next question. What were they being fed? This is kind of how we conduct the diet survey, is we wait for a bird, or we look around for birds that have fish, and the camera's kind of slow to respond. It's kind of like a weird video game. Where you have to zoom in and adjust and zoom in. But so someone observed that there's a fish and they're doing their best to find that fish. This may or may not be me. But you do your best to get in as close to the fish as you can to see the whole body in the overall form, and then also get in for some details. I don't know if Scott, can you ID this one? I get to frame by frame through it and pause, so actually it's a cod. But anyway, we basically get in there and try to get a very nice zoomed in photo of the fish, or multiple frames, and then at some point the chick will eat it. And that chick actually did eat that fish, which is impressive. So what did we find in terms of prey composition across the years? So you can see from the black, that's smelt. And in most years, smelt was the dominant fish. And then the second most common fish would be rockfish. And in some years, smelt and rockfish could make up to 80% of the diet. Salmon has is the third most common, but in some years is not really a big deal at all, and is nothing compared to rockfish and smelt in terms of importance. But you can see in 2016, there's an abrupt shift to more anchovy, and then in 2017, I only saw 4 fish. So you can see there's sample size at the top. I put it in there because that's all the fish that we saw that year. We were looking really hard for fish, and that's what was there. So it's really limited and anecdotal. Like, to say that anchovy was dominating in 2017 is hard. I would say more likely there was just not a lot of fish to be had in that year. But in general, at Castle Rock, what we see is smelt and rockfish. And then this transition to anchovy in 2016 and 17. So in terms of the other prey, we've seen 20 distinct prey types. Sometimes we can't get it to species, but there are some things that are distinct enough that we can. So the second fish down is a spotted cusk eel. And we thought they were gunnel, but then we had seen actually the modified pectoral fins. So we could see they were actually going to the bottom and getting up these cusk eel. Another thing they eat right below the squid is herring and typical fish, sardine, anchovy, cod. There's the cod, flatfish. So we've seen a myctophid, which, you know, they come up late at night, and sometimes in the morning, MERS can catch them before they migrate back down to the deep. And lingcod. So anyway, there's a diversity of prey that we see at the island that doesn't show up when you just start talking about the main components. And in terms of breaking down the composition of the prey by similarity across years, this is a non-metric multidimensional scaling. So basically, each survey in each year was broken down into a measure of similarity to other surveys, and then you can use all this data to kind of create a picture of which years are made up more of what, and what species are contributing to differences between years. So you can see in 2009, which is that orange circle, it's kind of off to the side, and it's more dominated by snailfish and cusk eel, like the weird other types of prey. Whereas in the center, so 2008, is this big red circle, and it's defined by the typical smelt rockfish. So the species that are within each circle kind of help indicate what's driving differences in each year. So 2016, you can see anchovy way on the bottom, and that's driving a lot of the difference that we see in 2016. So if we were to kind of break this down into foraging, or fledging success, which years are good, and what does the diet look like? All the good years are kind of clustering around the normal prey. And then 2007, the moderate year, is kind of deviating from that normal, incorporating more anchovy. And then 2016 is very distinct diet. And because I only had 4 fish in 2017, I kept that out. But basically, with all this work, what have we learned? And basically, we did find what we expected in terms of our predictions. So in terms of nest initiation, we found that it was timed to follow upwelling. So the timing of upwelling accounted for 60% of the variability in nesting phenology of MERS, and provided evidence that MERS are sensitive to and can alter the timing of nesting to match the peak availability of prey. In terms of their reproduction, what we found was MERS are either going to have a good year or a bad year, and there's not much in between. And that's typical from other colonies. We would expect that. And at this colony, a primary factor influencing reproduction was prey abundance. So despite MERS timing their nesting to coincide with this greater abundance of prey in the annual cycle, availability was barely sufficient to meet the needs of the colony. And in every year of this study, we could tell MERS are working hard to find enough prey for their chick for the whole time. And they're basically approaching the limits of their ability to behaviorally compensate. And once they cross this threshold to compensate, that's what results in widespread nest abandonment and chick starvation. And then while you could see the diet was relatively stable in terms of composition across the years, in recent years, there's been a shift to anchovy. And it's hard to say if that shift has caused poor reproduction, because Murres eat anchovy down here, and they do just fine. So I don't really want to attribute a shift in prey to them having poor reproduction, but it just indicates a change in the marine system that's atypical for this area. And the bottom line is chicks have to be fed multiple times per day. So, but like us on finals week or getting ready for your defense, you can only work so hard before you run out of time. And that's true with Murres. There's only 24 hours in a day, and you can only fly so far and search so much. So one real sign of like hitting this behavioral limit, like the point at which Murres can no longer compensate for reduced prey, is when chicks get left alone. Which is why I think it's so rare at other colonies, is because this is a condition that once it's hit, it's kind of very easy to cross over into widespread failure. And there are a lot of reasons, a lot of things that happens to chicks when they get left alone. Like I said earlier, they can be eaten by predators, which is that's what you would think would happen. But neighbors can also kill chicks, which hasn't been observed very frequently. Let's see. I have this video. If you look in the bottom of the screen, you see this chick getting thrown around. Because that's what happens when chicks get left alone and a parent's trying to feed their own chick and an unattended chick is nearby. They'll actually throw them around and can definitely end up in a fatal situation. And then as a last resort, so let's say you didn't want to leave your chick alone, we've actually seen this quite frequently at Castle Rock, is you can actually just stay at the colony with your chick, and if your neighbor brings a fish in, well, you can steal it. Then you don't have to leave. So this actually happens every single year at Castle, and it's a lot more common than we ever expected it would be, especially based on publications. There's one publication about fish stealing. So if we look at the occurrence of these things elsewhere, there's been one publication about Murres basically killing each other's chicks, and that's from 2008. And then another one about fish stealing in common Murre during a period of poor prey food availability. And these are both from the UK, where the marine system is a lot less dynamic, and the prey base is pretty much a lot simpler. So there's only a couple of prey species that Murres feed on there. And if that prey is not available, it's not like they can just switch to anchovy or rockfish. It's like if that prey is not there, they don't have it. So it's a very different situation than what we have in the California current. So to kind of get at maybe a little bit better what was happening in 2016 and 2017 specifically, other than the fact that the colony is already operating at this edge of like just barely able to pull it off, is perhaps there's too many Murres. This is an aerial photo of Castle Rock, and all the gray is just tens and hundreds of thousands of Murres. And based on a study published in a report in 2017, if you look at the time since my study began, so this is 2007 to 2014, this is the population numbers at Castle Rock, and across the whole island, it's been growing at a rate of 5.2 to 6.4%, and we don't know if it's continued through time or if it leveled off, but this increase in birds can definitely contribute to having less food available. So that's one idea. Perhaps it's too many Murres. Another possibility is changes in marine productivity. So just briefly, here's kind of the last 5 years of State of the California Current titles, and you can see for a long time we've kind of been hinting at something happening in the Northern California Current system. In 2013 and 14, there's El Nino looming, and El Nino is a time where seabirds often don't do well. It's associated with warm water and less productive conditions. So if you're a seabird biologist, 1983, 1997, 2006, 7, these timing of El Ninos are often coinciding with times where seabirds don't do well. So you have the El Nino in 2013 and 14, the warm water blob 2014-15, comparing to the 1997-1998 El Nino, and then still anything but normal in the north for 2016-2017. And then this is the most recent one, so it's still a draft, but the title is still not quite normal in the north, so, but seems like it's getting back to a more cold water dominated regime. So one question is, do what we see with common murres, is that applicable to other seabirds that nest at Castle Rock? And I would argue that it is applicable. For some species don't necessarily eat fish. A lot of them do eat fish, but they're all nesting at the same location at the same time. And basically they're all relying on the same environment while they're nesting. So basically there's, for the fish-eating birds especially, there can be a great overlap in their prey base and the foraging environment of murres and other species. So, and this is known from the Farallones where they studied prey base overlap, and especially in really good years, birds can all be eating the same type of prey, and then in bad years they kind of tend to separate what they're foraging on to minimize overlap. But each of these birds can only travel so far from the island before they have to return, and they are depending on the water that's surrounding the breeding colony. So one thing that we learned is that the California current system is dynamic. So what we see at Castle Rock is not necessarily what they see at the Farallones, and is not necessarily what they see to the north at Yaquina Head, which is the other place where monitoring happens. Behaviorally, right away, there's some key differences, specifically the foraging effort. Like I said, what we see at Castle Rock in terms of how hard they're working, leaving their chicks alone and stealing fish from each other, are very different and not typical of what's seen in a California current system colony. Dietarily, I don't have a figure, but at the Farallones, it's a lot more rockfish and not a lot of smelt, and then it can switch between rockfish and anchovy. But what we see at Castle Rock is more similar actually to the north. So what they see at Yaquina Head is often smelt and Pacific sand lance and things that we're more likely to see. So yeah, dietarily, Castle's definitely different. And it's just important if you're trying to manage fisheries to take account of what's going on at Castle Rock, because if you have 100,000 murres eating 100,000 fish, and their chicks are eating 100,000 fish every day, that adds up to a lot. And if you think they're eating anchovy, but they're not, they're eating smelt, I mean, this all adds up when you're considering population dynamics of prey populations. So I think my main take-home point is the California current system is dynamic, and Castle Rock is an essential part of painting that picture. It's in a unique location, and we can learn things about the California current system by seeing how murres do at this colony, how hard they work, and what they eat. And because of this delicate balance that exists currently between prey availability and the needs of seabirds that nest here, even small shifts that cause demands to exceed energy availability will likely result in large-scale reproductive failure for both Murres as well as other seabirds. And if we aren't checking out this colony from time to time, there's no way for us to know how well birds are doing. So with that, I would like to thank all the collaborators. So this is a very long, difficult project. I can't do all this all by myself. The original gang is with the boat, so Rico Whiteley, Jerry McChesney, who's the Farallone's refuge manager, and Eric Nelson, who's kind of behind laughing. He's the Humboldt Bay National Wildlife Refuge manager who manages Castle Rock. These are the people that were really integral to getting this project started. They were there as early as 2000 and up through 2005, just laying the groundwork for this. We've had help from the Coast Guard to get to and from the island at times, and the guy in the corner, Conrad, he's actually the guy that designed the camera system. He's a fisherman, he's a salmon fisherman in Alaska, and him and a group of friends, as far as I know the story, made these cameras because they did something unique, and even after they retired the company for years, I'd be like, Conrad on his personal phone, please help me fix this, and it works on XP, so, I mean, this technology is like from 2000, and he always took my call, so very thankful. And of course, all the Vert Lab members, especially Mason, for doing a lot of the field work, and Jackie too, who's not here. But yeah, so with that, I'd be glad to take any questions. Jim?
So we know that in a colony that the capabilities of the birds differ within the colony itself. That oftentimes in the middle of colonies you'll have birds that are older individuals that greater capabilities. Is that true with birds? And if it is, the area you were looking at via the cameras, are you looking at a peripheral part of the colony or in the middle of the colony? And do you think, therefore, there's any differences? Are your birds that you're looking at representative of the whole, I guess?
That's a great question. At Castle Rock, if you look at the aerial photo, there's actually sub-colonies. So where we study is actually on the side of the island where there are fewer Murres. The main part of the colony is on the western side. We have the cameras positioned in one of the larger colonies on the eastern side, and it's right in the center. I have two responses. One is that just based on my observation, and I could be totally wrong, it feels like in these sub-colonies, if they're of a certain size, once you're in the center, those are kind of the more experienced birds, and birds on the edge, that's like suboptimal because you're a lot more at risk of gulls being right there able to get in. But I have been curious about that, and although I can't get detailed enough video, I can certainly zoom in to the main colonies, and whenever we're having widespread nest failure or success, I try to go and look at those other sites qualitatively to make sure they're on eggs. I don't quantify that, but yeah, I try to make sure that it's similar because that's something that we've always been worried about. So, and like in aerial photos too, in a year where they aren't doing well, you can see like a lot of the birds across the whole colony will be standing, like they don't have anything, no egg or chick. So, like I can't tell you for sure, but I feel pretty confident to say that what we're seeing is kind of representative of the rest based on, yeah, what I've been able to.
And do you know which species of smelt it is?
I wish. One time we thought we might have saw a longfin, but you know, smelt are really, really hard to ID, especially. I mean, basically, we're like, is there an adipose fin? If it is, it's going to be salmon or smelt, and then, but it would be good. I've tried to get otoliths off the island, not just from Murres, but from pellets of cormorants, and They disappear. I don't know where they go. Yeah, so.
So, what I learned today is that there's a lot of cons about being in a colony. There's competition for space, for food. Actually, the other birds preying on each other's chicks. What are the advantages? I mean, and so do you see any birds that are actually flying off the colony and trying to establish new colonies? Is there any? So what are the pros about being in a colony?
Yeah, well, in terms of birds establishing new colonies, seabirds are kind of, I can't talk about all seabirds, but I do know about a lot of alcids. They are attracted to each other socially. So if I were to have an oil spill off right and wipe out a whole colony, birds aren't going to just find that rock and go to it. They need other murres there to attract them. So that actually happened, and they put like murre statues in recordings, and murres, presumably young murres that weren't breeding yet, heard that, and they were like, oh, this is a place that we could potentially breed. But I think the colonies are kind of required. There's not that many places where a seabird can nest free of predators, and these offshore islands really are the only place that they have. So, and that's why island conservation efforts are so focused on eradicating invasive like rats that get on an island, because they can truly wipe out the whole colony. So I think, not that colonial nesting isn't a bad, so some benefits would be, okay, you're hungry, you went out, you found fish somewhere. I can see like what direction you came from, and I can go, oh, you have food over there. So, you know, you can get information at the colony about where it's good to eat. You do provide protection if the food's great. If food's great, you know, I'm not gonna leave my chick alone, and you're not gonna try to beat it up. So in most years where food is easy to come by, then it is what it is because it has to be, but also you're not gonna be having this kind of violence that we've seen at Castle Rock. Yeah. Does that answer you?
Yeah.
Okay.
Yeah.
Scott?
Do you have a sense for these, you're saying what's happening to the chicks once they leave the colony, you know, whether or not the bag, there's more carcasses washed up on the beach or anything like that?
Yeah, I think they definitely die, a proportion of them, when they get on the out on the sea. I don't know if it's a certain percentage every year, but on a year where you have a good year on an island, you'll have a lot more chicks washing up on the beach. So, but even if like 10% of the chicks don't make it once they get on the water, if it's 10% of 150,000, that's a lot of birds that look like they died. I mean, they did die, but there's still a lot of chicks out there. And then in a year where they don't produce chicks off the island, yeah, nothing shows up on the beach. Maybe adults do. But yeah, I will get emails from people, we're really worried, there's a bunch of dead chicks, how did they do? And I'm like, yeah, actually they did really well, so that's why there's all those chicks. But yeah, it's kind of counterintuitive, and I know John Pyatt and a couple other people are trying to really hone in on what happens once they leave. But yeah, it's harsh, the ocean's harsh. I'm sure it's really hard to be there 28 days sometimes, 15 to 28 days when they leave. It's probably not the easiest thing when they get out there. Tom?
Have there been any documented impacts of harmful algal blooms on these lakes? I know during the blog anomaly was a widespread. Could that be a possible factor in that years?
I'm not going to rule that out. I would say, I would think that if it was a harmful algal bloom, and someone correct me if I'm wrong, but if the adults are out there foraging in it, it would be the adults that are affected. And I've never seen adults acting weird or dying like at the island, and you know, I've never seen even a chick with an adult that doesn't come back. So I would say, in terms of chicks not making it, I would think primarily at this colony it's starvation. At other colonies it's not the case, so this is a point I didn't make, but one reason why I think Castle Rock is cool, right now at least, is everything is based on this prey availability in terms of how they survive. So when you go up to Oregon, all the colonies are failing. It may be that they don't have food, but really what's happening is eagles are predating murres and like flushing them off the island. So those colonies are not doing well either, but it's not because of this bottom-up prey base. And so I think Castle's really interesting because you can get an idea of marine productivity, whereas up north it's kind of like, maybe we would have known, but they all died because of eagles. So, yeah.
So I was thinking about your graph of the population on the island that's been increasing recently, and is that because the bird population has been increasing, or are they just more birds are just concentrating at this one spot?
So, from my understanding, that growth rate is faster than that colony could actually grow if it was just by reproduction alone. And what the thought is those colonies up in Oregon and Washington that are having this eagle predation, we think they're moving down to more southerly colonies, Castle Rock, and yeah, trying to nest there instead. And yeah, but yeah, I mean they do well at the colony in general. So only 2016 and 17 were aberrant. So it could be that they're growing and birds are coming in. But yeah, we'd have to do a better demographic study to figure that one out.